So now we have seen that what is the force acting on a horizontal surface, then vertical surface, and then inclined surfaces. All these surfaces were plane surfaces. But now let us see that we have a curved surface submerged in a liquid. So we have a curved surface. So let us take a curved surface here, and you can see this is a curved surface which is immersed in a liquid, and you see this is a curved area. So we have a curved surface here. This is small area. I say it is dA, and the pressure is normal to this. So we have a pressure force, say PdA. So this is the force acting on this. Now this force will have two components. I say this force here acting will have two components. So one along the horizontal and one along the vertical. So this is the horizontal component, this horizontal and this vertical. So this area, so now you see just how we get these components. So suppose, now let us see this, what is happening. Here we have a prismatic type. So this is the horizontal area and this is the vertical, and this is the curved surface. So what force P is acting here? This P has a vertical component and a horizontal component. You can see this magnified view. So I have this one, this area, this is the horizontal part, and you can see this is the curved surface area. This is the curved area, you can see. I am not shading it. So the force is acting along this. The fluid pressure is acting on this. So this fluid pressure force will have two effects, one on this and another on this. So that is the on the vertical face as well as the horizontal. So we will separately calculate the components of this fluid force along horizontal and along the vertical. So let us calculate along the horizontal, and so first we will calculate along the horizontal force. Now we have seen that the force on the curved surface area will have two components, one along vertical and one along horizontal. Let us first see what will the force along the horizontal. So you see, this is the curved part. Suppose I say this is my curved part. So what we do, we take its projection here on the vertical. So you can see this is the projection on the vertical. So this area, or this is the projection on the vertical. So you see this point, that the pressure force here is P into ds. ds is the curved surface area, and this curved surface area has projection along the vertical as well as horizontal. So you see here, this is ds, and suppose this I am showing you this view. This is dA present here along this. So this shaded area is suppose dA, and this is theta. So we have dA is equal to ds into sine theta. Now you see here, this is the force acting, and you see the angle here is theta, this theta. So this theta, this is the theta. So we have this angle as also theta. So now you see here, this pressure force is here. So just you see, this is the curved surface. I'm just drawing the trace, and you have a pressure force P into ds acting. I am interested in this horizontal component, and this is the vertical direction. We know that this angle is theta. So if this angle is theta, so you can see that this angle is 90 minus theta, and so you can see this angle theta, so this becomes 90 minus theta. So component of force on curved surface along horizontal. So we are interested in calculating that dF force along horizontal component. That means we have dF times cos, this horizontal component will be dF force, this is dF force, that is equal to cos 90 minus theta, that is dF sin theta. Now this is dF along horizontal, so dF along horizontal is equal to dF is P ds into sin theta. Now you see ds sin theta is nothing but dA. What is dA? The projection of the curved surface area on the vertical. So on the vertical. So if I want to know what is the total force acting on this, so thus our ready-made formula is thus the component of force on the curved surface along horizontal is equal to the pressure, the area of projection on the vertical. So this is only for the differential force, because the force may be changing with height. So in that case we have to again do the integration. Let us see how we can do it. So now suppose we have a plane area, that is the projection, and this is the curved surface. So this is the curved surface part. So you see this part is actually in the liquid. So you get a force, the force will be like this. Here the force will be large, and here the force as you go up it will be less. So the total force will have two components, one F vertical and another F horizontal. So what the theory tells, the horizontal force on this curved surface area is the total force acting on the projection of the area. And how to calculate? So the total force on this projected area is, that is y bar. Suppose this is the center of mass of this projected area, y by var rho g into this area. So this area A, that is the projection area A. So the formula becomes the total force acting on the curved surface along the horizontal is the total force on the projected area on the vertical. So this we are writing as the formula, very important. The horizontal component of the total force acting on a curved surface submerged in a liquid is equal to the total force acting on the projection of the area on the vertical plane. So whatever the force will act on this projected area, that will be the force on this. Let us see the illustration of what formula I have developed. This is the free surface of a liquid, inside it which we have a three-dimensional object submerged. Now let us take a horizontal element on it. So here you see this is curved surface. So just I have shown you this. So now you can imagine that this curved surface has this area, and you can see this area. So we have two small areas. So this and this. Now you see the cross section of this area is this one. This shaded one is the cross section. Now the force acting here is in this direction, and this is P into ds1. This area is ds1, and the force acting here is here P, and that is ds2. Since they are at the same level, so they have the same pressure. So we have different force normal to these surfaces. So I call this df1 and I call this as df2. df2 is equal to p ds2. Now the horizontal component of df1, df1's x component will be P, the pressure P into the projection of this area, you see, which is dA. The projection of this area is dA, and df2 along x is again the projection of this area is dA. So these two are equal thus. That means thus there is not going to be any horizontal contribution of force from this and this. These two balances. So thus there is no unbalanced force, unbalanced pressure force along horizontal in a submerged body. So if you immerse a body inside a liquid, then there won't be any horizontal component. The only component will come out because of vertical. So horizontal contribution is zero. So there is only an upward buoyant force, never a vertical buoyant force, because the projection area of this and this is the same. So PdA is the same. Now let us calculate the component of force on the curved surface along vertical. So here this is the vertical free surface of the liquid, and this is the curved surface. Suppose I say this is the curved surface. So we have taken a small element here. Suppose I have taken a small element of ds area, which is curved surface. So the pressure force acting is actually in this direction, that is P into ds. So I am interested in this is the force F, that is the horizontal and the vertical component. So dF along the vertical is equal to dF the angle. So now you see, just see this area ds, and this time this theta. So this is the area dA we are talking about, dA along x. So this is the projection on this horizontal plane, and suppose we have a pressure like this. So this pressure force is like this. So we need this angle. This is theta, 90 minus theta. So this angle is theta. So we have to take this dF cos theta. And you see this dF, vertical dF is the pressure P times the area ds into cos theta. So that comes out to be P ds cos theta is dA, this area. Now suppose I write P as h rho g. H rho g is, h is the height of this portion. This portion has a height h from the free surface. So we have h rho g dA. So dFV will be h here rho h dA times g. Now you see this is the area. Let us remove this. So we have this as dA area, and into h, dA into h is nothing but the volume of this prismatic element. So this volume of this whole liquid up to this prismatic element. So volume of this prismatic element is HDA into this. This is the mass of the water on the prismatic element which extends to the free surface of liquid. This is this much mass. So if the total vertical force is that, this is integration of this quantity, that is the total, it does, this is the weight of the liquid above the curved surface area and below the free surface. So thus the total force will be the total weight of this liquid within this volume. So above this surface area and below this, whatever liquid weight is there, that force is the vertical component of the force on the curved surface.